Hi there, this is Mr. Schnitzius, and in this video we're going to cover numbers 16 to 30 from the North Carolina end of course geometry assessment. Number 16 says a regular tetrahedron is a triangular pyramid. What is the total surface area of a regular tetrahedron with base edges of 7 centimeters? Well, we saw this in a question in the last video, but to be regular means that all the side lengths are the same. So a tetrahedron is a three-dimensional object. So this means that all, actually need to take away this one. All the edges of this triangular pyramid are congruent to each other. So in the base, there are 3 7-centimeter lengths. There's also these 3 7-centimeter lengths that are coming together to make this vertex up at the top. So in the base, we've got a 7 by 7 by 7 triangle, but we also have that for each of the lateral triangular faces. So I think for me, since this side is 7 centimeters, the back side on the bottom is 7 centimeters, this side right here is 7 centimeters. So for this problem, instead of using the surface area formula, which we could do, there's maybe two different ways that we'll work out this problem. So they want the total surface area. So that means using this formula right here. Well, as you can see, the slant height of this triangular pyramid is the length that we have right here, perpendicular to the 7-centimeter base. Well, we know that if this is an equilateral triangle with sides of 7 centimeters each, all three of those sides are congruent. 180 degrees divided by 3 gives us 60-degree angles for each of these angles. So we've got 60 degrees, 90 degrees, and this 60-degree angle gets split into two 30-degree angles. Hey, we've got two 30, 60, 90 triangles. Well, if we break that down to the way that we label a 30, 60, 90 triangle, this length would be 2x. Across from the 30-degree angle would be x, so half of 7 centimeters would be 3.5 centimeters. And then across from the 60-degree angle is x times the square root of 3, which would be 3.5 times the square root of 3 centimeters. So that is the slant height. So to get the total surface area, we also need the area of the base. Well, this slant height, 3.5 times the square root of 3 centimeters, is also the height of the base. So to calculate the area of the base, we would want to do 1/2 times the base length times the height of the base. Well, that would be, that would be 1/2. The entire length of the base would be 7 centimeters. The height of the triangle would be 3.5 times the square root of 3 centimeters. So since all these answers are in terms of the square root of 3, we're going to try to leave this as the square root of 3. So we need units there. So how many square roots of 3 is that? 1/2 times 7 times 3.5 is 12.25. So that's going to be the area of the base is 12.25 times the square root of 3 square centimeters. Okay, so we're just about ready to solve this problem out. The total surface area, according to this formula, is 1/2 times the perimeter of the base. Well, that's pretty easy. The perimeter of the base is 7 centimeters times 3 would be 21 centimeters. 1/2 times 21 centimeters times 3.5 centimeters. Sorry, 3.5 times the square root of 3 centimeters. Plus the area of the base that we got right here, which was 12.25 times the square root of 3 centimeters squared. So let's see what this comes out to. 1/2 times 21 times 3.5. So that's 36.75 times the square root of 3. Centimeters squared plus 12.25 times the square root of 3 centimeters squared. So altogether that gives us 49 times the square root of 3 centimeters squared. All right, and if you look carefully, you might notice that these 4 faces that make up this triangular pyramid are all congruent. So we also could have just done 4 times the area of one triangular face. That would be a way to get the surface area a little more quickly. All right, number 17 says a translation is applied to triangle FGH, forming triangle F prime, G prime, H prime. If the translation is described by x prime, y prime equals x plus 2, comma, y minus 3, which graph shows the translation correctly? Well, this translation notation is saying that if we add 2 to each x value, we're going to translate 2 units to the right. So let's see if we can find one where the new points for F, G, and H are not to the right. Here we're shifting to the left, so it's not A. Here from F to F prime, we're shifting to the left, so it's not C. We're shifting to the right. We're shifting to the right. Okay, so it's down between B and D. How do we know which one of those to choose? Well, we need to translate 3 units down on the y-axis. So if we look at the coordinates for point F, let's say F starts at 1, 3. 2 units to the right would mean we wanted to go from an x value of 1 to an x value of 3. So that happens for F prime here. That does not happen for F prime here. Going down 3 units would mean we would want to translate to a y value of 0, which is actually what we've done here. So just by looking at one point, we can see that the answer to number 17 is B. Number 18, the vertex matrix for triangle PQR is this. Now, vertex matrices are not going to be covered on the final exam, so we're not going to go over this question in as much detail as we could, but I did want to show you some helpful information that you could have gotten out of this problem. We've got triangle PQR and its image, triangle P prime, Q prime, R prime, after a transformation. Well, each pre-image coordinate is multiplied by a scale factor of 2. You can see that pretty easily. 2, 4 goes to 4, 8. Those are both doubled. 3, negative 3 goes to 6, negative 6. Those are both doubled. Same thing with negative 2, negative 2. Sorry, that should be that the new point P is at negative 4, comma, negative 4. So whenever each pre-image coordinate is multiplied by the same scale factor, this is an example of a dilation centered at the origin, and the scale factor is simply what you multiplied each pre-image coordinate by. Since this scale factor is larger than 1, that's why this is an enlargement. That's a dilation centered at the origin using a scale factor of 2. All right, number 19, if triangle SLM is rotated 180 degrees about the origin, what will be the coordinates for the image of M? This is another one where you can pretty simply just use some common sense and some elimination of wrong answers to get your answer pretty quickly. Right now, we're in quadrant 4. And each of these quadrants on the axes is 90 degrees away from the other. So another way of saying that is if we're on the positive x-axis and we rotate 90 degrees counterclockwise, now we're on the y-axis. If we're on the y-axis and we rotate another 90 degrees counterclockwise, now we're on the negative x-axis. Another 90 degrees, now we're on the negative y-axis. Another 90 degrees counterclockwise, now we're back on the x-axis. Well, it's the same thing when you're starting not on one of the axes, but at a point. If we start here at point M and we rotate 90 degrees counterclockwise, we're going to be in quadrant 1. But we don't want to be in quadrant 1 because we don't want to rotate 180 degrees. Sorry, we don't want to rotate 90 degrees. We want to rotate 90 degrees and then plus another 90 degrees to get 180 degrees. So from here, a 90-degree rotation would get us in quadrant 1, then another 90-degree rotation would get us in quadrant 2. So our answer choice needs to reside in quadrant 2, and that's convenient because there's only one answer choice in quadrant 2 where the signs are negative for x and positive for y, and that is answer choice C. And don't worry too much about knowing, well, am I supposed to rotate counterclockwise or clockwise? Because when you're dealing with 180-degree rotations, it comes out to be exactly the same. Rotating 90 degrees into quadrant 3 and then another 90 degrees into quadrant 2 will give us the same result. And just to show you what that point would look like, the point negative 5, 5 is about here. So you can see if you connect those 2 points, that segment that connects them passes through the origin, and the angle that you get is a 180-degree angle because that is the measure of a straight line that connects them. So that's why we say that that rotation is about the origin, because that is the point that we're using to draw the connecting segment or segments joining those 2 points. Number 20, again, vertex matrices are not going to be on the final exam, so don't worry about this. But what I did want to show you here is that triangle JKL is translated 2 units right and 3 units up, resulting in triangle J prime, K prime, L prime. And then after that, we do a translation of 4 units left and 1 unit up is applied to triangle J prime, K prime, L prime, resulting in triangle J double prime, K double prime, L double prime, which matrix expression gives the vertex matrix for triangle J double prime, K double prime, L double prime? Well, if we translate 2 units right and then 4 units left, that's in total the same as moving 2 units to the left. In transformation notation, the way to show that we're moving 2 units to the left would be to take each x value and subtract 2. But we're supposed to do the same thing vertically. If we translate 3 units up and then another 1 unit up, that's the same as translating 4 units up. How do we show that in transformation notation? Well, that would be y plus 4. So that would be the way to, in transformation notation, show the end result of this composition of transformations. Number 21, in order to win a game, Sheila must spin a 7 on the spinner below. If the spinner is fair, what is the probability that she will spin a 7? Well, I put geometric probability equals shaded area over total area. They didn't tell us what the radius here is, and that's perfectly okay, because here we can simply just do the ratio of the total number of degrees as the whole, and the number of degrees that are in our shaded portion as the part. So for us, that would be 30 degrees for the part that's a 7, divided by 360 degrees. This is that same part over whole relationship that you want to think about when you're doing geometric probability. So we can try to reduce that. Those zeros cancel out and we get 3 over 36. We can divide the top and bottom by 3. 3 divided by 3 is 1, and 36 divided by 3 is 12. So that is how we get 1 over 12 part A. All right, number 22. Billy is 74 inches tall. So here's Billy, that's his height, 74 inches. And his shadow down here along the bottom is 70 inches long. What is the approximate angle of elevation of the sun? Well, this angle right here is the angle that we're looking for. If we're assuming that Billy is standing straight up and down, sorry that he looks like such a ridiculous stick figure, then the angle that he makes with his shadow is going to be a right angle. And since we have a right triangle formed here, we can use trigonometry to figure out this angle of elevation. So we're going to label our legs. This is going to be opposite, 74 inches. The leg next to the angle that's marked is the adjacent leg. And so we want to remember that the tangent of this angle equals the opposite leg divided by the adjacent leg. And that's telling us that the tangent of this angle x is 74 inches over 70 inches, which means if we want to find that angle, we just need to do the inverse tangent of 74 over 70. Well, let's see. Let's make sure that we're really in degree mode. We are. So we want to do the inverse tangent of 74 over 70. And that gives us that big UFE calculation, but that's actually 46.59 degrees, which rounds up to 47 degrees. That's how we get C. Number 23 says the perimeter of a regular hexagon is 48 feet. What is the approximate area of this polygon? Well, we know that we can use this area formula for a regular polygon. The area of a regular polygon is 1/2 times the apothem times the perimeter. So this is actually really, really good news. We already know the 1/2. We need to figure out what the apothem is. We already know that the perimeter is 48 feet. Well, in order to figure this out, we need to figure out the length of one side. And if the perimeter is 48 feet, dividing that by 6 will give us the length of one side, which would be 8 feet. So we know that this regular hexagon is split into 6 congruent triangles. And we also know that if we want to find the measure of these central angles, taking 360 degrees and dividing by how many triangles there are will give us 60 degrees for the measure of one of these angles. But we also know that each of these radii for the regular hexagon are the same. So in this isosceles triangle that we're going to use to solve this problem, let's draw that out here. We know that we've got a 60-degree angle on the top. Well, how many degrees are left over for these two base angles? Well, if these two sides are the same, these two angles have to be the same. We've got 120 degrees left over, and we need to divide that into two. So we're going to have 60 degrees here and another 60 degrees here. Well, this is an equilateral triangle. So if this is an equilateral triangle where all three sides are 8 feet, and we need to find the apothem, which is the distance from the center of the hexagon to the midpoint of one of the sides at a right angle, that would be the height of this equilateral triangle. Well, how do we find that? We can split this up into a 90 degree, 60 degree, 30 degree triangle where the hypotenuse is 8 feet. That's labeled 2x. This point here is the midpoint, so this 4-foot side across from the 30 degree angle is going to be labeled x. And we label the side across from a 60 degree angle in a 30, 60, 90, or 8 triangle x times the square root of 3. So if x is 4 feet, then this is going to be 4 times the square root of 3 feet. So for that apothem, we can plug in 4 times the square root of 3 feet. And let's put this in the calculator and see what we come up with. 1/2 times 4 times the square root of 3 times 48. So that gives us 96 times the square root of 3, which as a decimal is 166.27. So that rounds down to the nearest whole number to be 166 square feet. All right, number 24. A plastic tray is shown above with the dimensions labeled. The tray does not have a cover on top. The bottom and 2 of the sides are rectangles. The remaining 2 sides are congruent isosceles trapezoids. What is the total area of the outer surface of the tray? Well, we need to find the area of 5 different polygons. Since there's no top, we need to find the area of the 2 trapezoidal bases, which I'm going to outline in purple. We also need to find the area of 2 of the lateral rectangles on the side that are outlined in blue here. And we also need to find the area of the bottom lateral rectangle, which is highlighted in red. All right, so let's get to it. So what's the area formula for a trapezoid? That area formula is 1/2 times base 1 plus base 2 times the height. So what are the 2 bases? They're the parallel sides. That would be 18 and 12. So 1/2 times 18 centimeters plus 12 centimeters times the height. The height is the perpendicular distance between the 2 bases. So that's going to be 4.5 centimeters. So let's see what that area comes out to be. 1/2 times 18 plus 12 times 4.5. 67.5 square centimeters. But we will multiply that times 2 because there are 2 of those. and that's going to be 135. That's the total area for the two trapezoidal bases, 135 square centimeters. Then we want to do the area of the two side lateral rectangles. Well, that's going to be much easier. That's simply base times height. So for these blue rectangles, we've got a base of 20 centimeters, a height of 6 centimeters. So that's 120 square centimeters, but we want to multiply that times 2. Gives us 240 square centimeters. And now we want to do the area of the bottom lateral rectangle. So that's going to be the same area equals the base times height. So the area is 20 centimeters times 12 centimeters. So that's 240 square centimeters. So now if we total everything up, we've got 240 square centimeters for the bottom lateral rectangle, plus 240 square centimeters for the two side lateral rectangles, plus 135 square centimeters for the area of the two trapezoidal bases. And that all comes out to give us 615 square centimeters. Number 25 says a container in the shape of a rectangular prism has a base that measures 20 centimeters by 30 centimeters and has a height of 15 centimeters. The container is partially filled with water. A student adds more water to the container and notes that the water level rises 2.5 centimeters. What is the volume of the added water? So what we've already got drawn out here is the water that's starting in the tank. Length of 30 centimeters, width of 20 centimeters, height of 15 centimeters. It's not asking us to get the volume of the original water. It's only saying if we add another 2.5 centimeters worth of water, add another 2.5 centimeters worth of water, and only calculate the volume of the water that we've added in here, what would that volume come out to be? Well, how do we find the volume of a rectangularly prismed shape that we have here in what's labeled in red? Well, it's going to be the length times the width times the height. So the area of the base is going to be that 30 centimeters times 20 centimeters. But we need to multiply by the height only of what we added, which is 2.5 centimeters extra water. And whenever we multiply those together, it is going to come out to be 1,500 cubic centimeters, which is why we get a volume of A. Number 26, a truck is at the top of a ramp as shown below. Approximately how high above the ground is the truck? Well, I should have done this on the problem about the angle of elevation. Here is what it's going to show you on your formula chart on Thursday for the sine, cosine, and tangent ratios in a right triangle. Okay? And we can make a right triangle in this problem if we say that the height that we're looking for is right here. And I'm actually going to change that to an x. Why is that? Well, we need to label our sides that we either know or we're looking for relative to this angle. So the reason I changed this from h to x is because I want to label this 4 meter length the hypotenuse. This side that we're looking for, the x, is opposite the 26-degree angle, so we want to use sine. And the equation that we're going to write is going to be the sine of 26 degrees equals x divided by 4. So once we've got this equation set up like this, it's actually really, really simple. We just need to get x by itself. So what's the opposite of dividing by 4? That would be multiplying both sides of this equation by 4. So x is going to be, in our calculator, 4 times the sine of 26 degrees. And as a decimal, that's going to come out to be 1.75, which is how we get the 1.75 meters. All right, number 27. In the figure below, ray SR is parallel to ray UV. So I already marked that one here. What is the measure of angle STU? Well, the best way to do that is to enclose that angle in to where we have a right angle right here. So how does that help us? Well, we know if we have a right angle here at the top, we also have a right angle here. And so we can do 140 degrees minus 90 degrees tells us that we've got 50 degrees left over for this angle here. So now we've got a quadrilateral made up of vertices S, T, U, and I'm going to put B. So that spells something. So that spells stub. So what do we know is true about the sum of the interior angle measures in this quadrilateral? Well, they have to add up to 360 degrees, right? So we've already used 100 degrees at point S, 90 degrees at point B, and inside the quadrilateral, 50 degrees at point U. So that is 240 degrees. Take that away from the 360 degrees that we're supposed to have in total, and that gives us 120 degrees. That is how we get C. All right, number 28. Ray OX is the bisector of angle WOZ. So right away, we know that this ray is splitting angle WOZ in half, and ray OY is the bisector of angle XOZ. So we're going to start out by marking that angle XOY and angle YOZ are congruent. And it tells us that the measure of angle YOZ is 26.5 degrees. Well, since we mark these two angles as congruent, we may as well mark angle XOY also 26.5 degrees. And they want to know the measure of angle WOZ. Well, if this is true, then that's telling us that angle WOX is congruent to angle XOZ. What's the measure of angle XOZ? Well, it's twice 26.5 degrees. There's two 26.5 degrees. We can add those together to get 53 degrees. And so to answer the question, the measure of angle WOZ is 53 degrees plus two 26.5 degree angles, and that is how we get 106 degrees C. Number 29 says, given parallelogram EFGH, what is the length of side EF? What do we know about a parallelogram that could help us in this problem? Well, we know that opposite sides of a parallelogram are congruent. So we know that side EH is congruent to side GF. We also know that side EF is congruent to side GH. Well, if sides EH and GF are congruent, we can write this equation, 3x plus 6 equals 27. This is a pretty easy equation to solve. So we've got 3x equals 21, and we can divide both sides by 3. And that gives us x equals 7. Well, if x equals 7, we can use that to help us figure out the length of side HG. So that's 2 times whatever x is plus 5. We can substitute 7 for x. So 2 times 7 is 14, plus 5 more is 19. And since the length of segment HG is 19, so is the length of segment EF. So that's how we get C. All right, number 30. Given that angle VYX is bisected by ray YW, the measure of angle VYX equals 6R minus 18 degrees, and the measure of angle VYW equals 36 degrees. What is the value of R? Well, if angle VYX is bisected by ray YW, these two angle measures are going to be the same. They tell us that the measure of angle VYW is 36 degrees, so is the measure of angle WYX. So that's telling us that the measure of angle VYX is equal to 36 plus 36 is 72 degrees. So we know from here that the measure of angle VYX is 72 degrees. But they also told us that the measure of angle VYX is 6R minus 18. So now we can just set up this equation. 6R minus 18 equals 72. This is an easy equation to solve. We can add 18 to both sides. We get 6R equals 90. And when we divide both sides by 6, we discover that R equals 15, which is how we get answer choice A. All right, that's it for this video. Good luck studying for your final exam.